Good morning, everyone, and welcome to the Trusted CI webinar for February 24th, 2025. I'm your host, Jeanette Dopheide. Trusted CI is the NSF Cybersecurity Center of Excellence, and these webinars are part of its mission to deliver high-quality, actionable guidance regarding cybersecurity to the NSF community. More information about Trusted CI can be found at trustedci.org. Today's topic is Trusted Volunteer Edge Cloud Computing for Scientific Networks, and our presenter is Prasad Kalyam. Prasad is a Curator's Distinguished Professor and the Greg L. Gilliam Professor of Cybersecurity in the Department of Electrical Engineering and Computer Science at University of Missouri, Columbia, and the Director of the Center for Cyber Education, Research and Infrastructure, also known as Mizzou's CERI, SERI, maybe? Is that what you refer to it as? Yeah. Great. Before we begin, I have a few things to note. First, this presentation is being recorded. Second, participants are welcome to ask questions during the presentation. I'll be following along in the chat, so you can go ahead and type those up. And with that, I will hand things over to Prasad. Prasad, welcome.
Thank you, Janet, and good morning to all of those who joined. I'm here to present our project, which is a NSF CC project. And I'm going to talk about trusted volunteer edge cloud computing relating to scientific workflows, which is kind of a topic we started working on 4 years ago. And in this talk, I want to present some of our findings and some of our recent work. And I'm hoping to hear a lot of feedback and suggestions from the audience. To kind of set the stage, what do I mean when I say volunteer edge cloud computing? So the idea is, obviously, scientific users today have a lot of data. They have lots of workflows. Many of them are becoming more ML, DL, like deep learning and machine learning based. There's a big demand for doing computation, and those computations are usually bursty, and a lot of data movement, data processing has to be done. So we have users with these needs, and obviously we have cloud platforms that have evolved to the point where it's pretty easy to set up cloud instances and have certain SLA service level agreements, have high availability. You have a lot of APIs to create secure and scalable configurations. You can have a lot of APIs to mix a lot of services. All of those positives are there, but cloud platforms tend to be expensive, first of all. Second, there is high latency if you're trying to push data in and out. And not to mention, there's also the proprietary nature of cloud platforms. So sort of alternate or complement to the cloud could be this idea of volunteer edge nodes, which are nodes that are in universities or available on the internet, where people are willing to give a portion of the resources, right? And they tend to be abundant because you can get a lot of volunteer resources, and something similar you can think about like the SETI and other kind of infrastructures where you can have people in a community, especially if they're all cooperating, to give up some resources for others to run some workflows. But those resources are obviously heterogeneous, and they come at a low cost in some sense, right? It's crowdsourced in some way, but they could have low latency if those nodes are close to you, or close to where the data is being processed. And today we also have interesting technologies like KubeEdge, K3S, where you can run workflows on whatever kind of machines, right? It's pretty portable to run workflows using Docker containers. But obviously, we have some unpredictability in terms of volunteer resources, because volunteers may choose to, not provide the resources, or, they're not always expected to give a certain SLA like a cloud provider does. So in essence, what I think the VEC computing paradigm is to kind of bring the best of all of the cloud platforms as well as the volunteer edge resources and create an infrastructure for science where we can have a distributed, geographically distributed, cost-effective infrastructure where we can run scientific workflows. We can have certain critical services in the cloud, but run a lot of the low latency, operations on these volunteer edge resources. So this is sort of the idea of volunteer edge cloud computing. And let's go a little bit more into like how this presents new research problems. And also there's probably issues of trusting these resources, probably the threats also that are involved in using these resources. And so we'll talk about that in terms of a research problem context. And then we'll talk about how we could have a reference architecture and some algorithms to address the trust and scheduling of these scientific workflows on these volunteer edge resources, and look at how to overcome some of the challenges, like I said, in terms of availability, which is basically intermittency of resources. It may not always be on if it's a volunteer resource, getting some reliability, some predictable performance, and last but not least, some security privacy guarantees if you can in these VEC environments. So that's what I'm going to talk about in this talk. And so diving a little bit more deep, right? We want to kind of look at what this paradigm can offer and what are sort of the bigger challenges to set up the research context. So as I said, the benefits obviously are there's abundance of these sort of low-cost resources. If you can find them close to the computing sites and the data processing locations, you can have low latency. It is in some sense distributed. You can make it resilient because you have, again, variety of resources that you can manage, and you can foster more collaboration, right, in the community. And you can scale also the science based on this sort of volunteer resources. So all of those are the advantages. The disadvantages obviously are, primarily around trust. So if I am a person who's running a scientific workflow, I get a volunteer node. How do I trust I can run it on that node, right? That it does what it's supposed to do, and it's going to give me some expected performance. And again, if I'm a owner of a volunteer node, if I'm giving it for somebody else to run a workflow, I'm worried about what will they run on that workflow, code that might affect my infrastructure. So there's obviously this kind of trust issue on both the scientific workflow owner as well as the volunteer edge provider, right? And also it's hard to have any governance issues. So you can't dictate policies for security or performance or cost or any of those things on the volunteer edge node. So it's hard to have sort of governance. And again, it's heterogeneous and it's a disparate set of technical configurations and specs. So you have to deal with creating an infrastructure that actually can serve some of the performance, security, privacy expectations of the scientific workflow users. So obviously there are positives and negatives, and I kind of was thinking, obviously we all understand it seems like a problem similar to the SATI problem many years back, but we have much more interesting and usable edge orchestration technologies, like I said, like CubeEdge, K3S. So it's definitely a new way to think about this sort of distributed computing, but also at NSF, there is this sort of initiatives, at least with the Open Science Data Federation, other sort of federations where the community is asked to share some of their resources. So in the Data Science Federation, if you get a CC star storage grant, you have to give maybe 20-30% of your storage to the community. And there is sort of this sort of central cloud service that is run by the OSDF path group that ensures through some sort of Kubernetes management, they can provide this sort of space for the community to use some larger storage, right, on these volunteer storage resources. So this model, I think, is definitely practical for the scientific community. And what we're doing in this project is going beyond this just storage, right? Thinking of compute, thinking of network, thinking of even services you can run on those volunteer nodes that ensure privacy and security. So I think if we can realize this volunteer edge computing paradigm on top of some of these sort of OSDF network cache sort of paradigms that are evolving through NSF support, we can actually build an infrastructure where we can have a ranking of resources. We can have some information on availability, predictability of those resources that can be used to then run trustworthy scientific computing workflow. So that's the big grand vision. And obviously, we had to look at how to make this provisioning efficient in the presence of unpredictable availability of resources, heterogeneous resources that are there. We have to make sure that the QoS requirements of the workflow user to some extent are satisfied in the presence of this intermittent or volatile nature of those resources and lack of governance and SLA policies. And last but not least, as I said, we have to address some of the threat models that go with this infrastructure, where inherently these volunteer resources are not trustworthy, right? So we don't have good security control. We are not sure how the data and code gets exposed, and more the scientific workflows are using machine learning models, lots of interesting data sets. So people are worried about who's looking at their code, who's having access to their models. So those are also threats that we need to establish, right, as problem sets to solve. And so if you look at what's already out there, as I said, yes, there are these orchestration technologies like K3S and KubeEdge, but not really schemes or frameworks that can look at how to quantify trust on these volunteer edge nodes and also come up with a way to schedule these tasks, right, in a way that can optimize resource allocation, maximize the availability, of these sort of volunteer resources in some sense. So think of this as managing clusters of these volunteer resources. How can I maintain availability in the cluster versus nodes can come and go, right? So thinking of those sort of cluster management for this edge cloud computing, is another interesting research problem. And last but not least, how do we make sure the workflows that run have some sort of privacy and security guarantees, right? So can we use some privacy enhancing technologies to make sure that there is some attestation and some way to have enclaves, right, that are going to have trusted execution of these codes. So those are all sort of the research problems we want to address. And what community are we kind of working with? I think the bioinformatics community is one that is very, very interested in this. So we've been working with this group which runs this KB Commons Science Gateway. There are more than 850 registered users, lots of different kinds of workflows that are being run with different kinds of computation and memory kind of requirements in these workflows, from simple workflows like RNA-seq to more involved workflows like PGen that uses Pegasus and HD Condor and others. So there's a variety of workflows that we're able to use in kind of testing this VC computing paradigm in our project. So we've been looking at some of these workflows as a way to look at diversity of the scientific workflows, looking at sort of the dynamic computational needs as these workflows are being executed, and also ultimately, how do we make this cost-effective, secure on this heterogeneous volunteer resources? So we've basically taken, and I'm showing one example here, these workflows and created these Docker containers that basically take different, you can call them functions that are supposed to be processed, in terms of pre-processing and post-processing of the data. So these Docker containers are something we can deploy through the K3S and KubeEdge services, and we're able to put our algorithms on top of it for, as I talked about, like for optimal resource allocation, ensuring some availability in terms of the intermittent volatility of resources, and also adding some privacy and security. So before I go more into some of the algorithms, I also want to say that we've developed a training module, which you can use as part of our Mizu Cloud DevOps, that actually shows you how you can take a bioinformatics workflow or any other sort of workflow, create a Docker container with certain functions within that workflow, and how you can deploy it in an edge computing infrastructure, right? This is something that's available on mizuclouddevops.net, and you're welcome to look at some of the other modules also we have, but we've created a sort of a learning module based on this idea of Dockerizing the scientific workflows and having the ability to orchestrate them, run them on some clusters with K3s and KubeEdge. So I welcome you to check this out. So in summary, the research problem, like I said, is to ensure that we can find trusted nodes and how do you define trust? So that's one of the research problems I'm going to talk more about. And how do we then match the requirements of the users with the performance and other sort of trusted capabilities of the edge nodes, right? So this matchmaking is another problem, right? And last but not least, dealing with efficiency, reliability, privacy, scalability, right, of these workflow execution. So those are sort of the things I'll talk next. Before I go into some of the algorithms that are going to be used to do these different, implementations of the reference architecture. So I will show you like what the reference architecture looks like. So as I said, we want to think about the idea of how we are building most workflows today, right? In this sort of machine learning, deep learning era we are in, where the heavy lifting, right? The heavy functions of these scientific workflows usually are done in the cloud, right? To a large extent, as much possible. And we have, again, predictability of resources. We have SLAs, we have governance on policies, we have APIs for flexibility, scalability. So we can do that. And then we still want to run a lot of lightweight inference or sort of pre-processing sort of steps, or in some sense, if you have enough scale of nodes, even larger processing on these edge cluster nodes that are managed by the edge hub in these K3s or KubeEdge infrastructures that treat these volunteer resources as part of like cluster nodes. And so we can build clusters at the edge with a lot of these abundant edge resources, and then integrate it with the cloud hub so we can run portion of resources on the cloud, and then we can use the volunteer nodes as much as they're available and as much they make sense for the scientific workflows to run the scientific workflows. So this is sort of the idea of the architecture, and it will require us to profile these edge nodes, right, in terms of figuring out what is their trust score, for example, right? So how are they in terms of reliability, if I want some sort of performance, or if I'm expecting security or even agility, can I run APIs on those nodes that can help me manage my workflows more easily. And so you take a number of these sort of volunteer hosts like I'm showing here, create these sort of clusters, and then you have to sort of look at how you quantify the trust. And if you can have sort of a list that is ordered based on the trust, right? So then you can have a scheduler basically that is able to figure out which of the workflow portions can run on those trusted nodes, right? It could be maybe smaller functions of the workflow, and then which should run again in the cloud, right? Which is able to run more heavyweight tasks. And so this is sort of the idea that the architecture will allow us to use the benefits of both the cloud and the volunteer edge, and we're able to have the preferences of the workflows matched to the best capable trusted resources on the volunteer edge side, and we can increase user satisfaction, reduce cost, and in some sense, by picking the nodes properly, we can even reduce latency of transfers and even processing of these scientific workflows. So let's now dig a little bit more deeper into what we think are some of the ways to solve these problems. There are obviously other ways. And again, we are also thinking of new ideas, but here are some ideas we've been experimenting on how to build this sort of trust model, how to think about scheduling those workflows across these volunteer nodes at a very large scale. And then after I finish that, I'll talk about some of the intermittency, reliability, privacy challenges being addressed. But we'll talk about now the trust part and the scheduling part. So how do we quantify trust? So this is a big topic. Like there are many, many ways to quantify trust of any resource. So we chose these PAX factors, and why is that is it's a sort of what I call as like non-functional requirements that end users will expect. So when they want to run a workflow, they expect certain execution times, right? So the performance is obviously a big factor of how they want to choose a particular node. And these workflows, as I said, have a lot of data, a lot of processing steps. So the agility or the ability to have APIs or manage these services around moving data, processing data, sharing data is also another factor. So agility is another important factor. Cost is obviously the other factor. For the provider perspective mostly, right? In terms of running the volunteer, resource for the workflows. But in some sense, there's also a cost you can think of from the workflow users in accessing the resource of the volunteer node and getting utility out of it, right? So there's sort of different kinds of costs you can think of. And last but not least, security and privacy. So can I run my workflow with certain security expectations? Maybe if I'm also sharing my data, or if I'm worried about the privacy of the data as it's being moved and also as it being processed. So those are also again factors. So these non-functional requirements of the workflow owners can be captured in these PAX factors. So when we say I trust a resource, we kind of want to connect it back to what would be the non-functional parameters that the owners would like, right? And if we can meet those requirements, it's success, right? Just you can say it's a trustworthy computation. So we chose these factors, and the idea is to really then understand the expectations from the application side, right, or the workflow side in terms of these PAX factors, and then matching them to the cloud and volunteer edge resources in a way those PAX factors are in some sense addressed when you, orchestrate or schedule the tasks, right? So that's the sort of goal of building this trust. And so the trust model, we've looked at it in many ways, but here's one way we published early on, one of the first works, is to think of a two-stage trust quantification. So one is at a individual node level, and then the second, as I said, is at a more cluster level, a global level. So as I said, the K3S or Cube Edge way of provisioning is to take all these edge nodes, create clusters, and then manage those, right, to schedule the workflow. So we looked at how we can take these sort of PAX factors, right? It gives us sort of a number of variables that we need to basically model to quantify the trust, and we're using a Dirichlet probability distribution function. So the higher the PD, we will say higher the trust, right? So we can do it at a sort of within a cluster level, and also across clusters, right? So at a node level and also at a cluster level. So we're able to compute this trust. And then once you have the trust, you can basically do the scheduling. Another recent way we quantified the trust is to use reinforcement learning. So what that does is you run some workflows on some nodes, you learn how they are executing, and you have some expectation of what those nodes should do. And based on them meeting or not meeting, right, using the reinforcement learning approach, we are able to again create a list of trusted nodes that can be ranked. So we have another method also to do that in a recent paper, which we published in UCC. And once you have that sort of trust score or way to rank the trust of these volunteer nodes, we can apply, in some sense, a scheduling algorithm that can schedule across a large number of these nodes. So we've done a particle swarm optimization based scheduler that we published. And what that does is basically, as you can see here, it looks at the behavior of the volunteer nodes, which is how we are kind of, in some sense, quantifying the trust. And then it uses that in terms of, as I said, the trust rank and sort of expected execution time, right? Which is one probably an easy thing to understand as a trust factor. So taking that and then assigning them on the volunteer edge nodes, right, to match basically the most trusted resources and most efficient allocation for a given set of requirements of the scientific workflows. So the two-step process of how we do the profiling and how we do the scheduling is sort of broken down here. So we established the initial trust initially based on the node spec, security settings, expected workflow performance. Using RL and some of the other trust scores methods, we can create basically a set of nodes that meet the expected execution times, and then we are constantly looking at how actually they're meeting it to keep revising their trust level, right? And then the scheduling is doing basically, in this case, we're using particle swarm optimization, so it can really scale very nicely across a number of volunteer nodes. And then we're trying to optimize the matching, as I said, of the PAX factors on the available volunteer nodes to meet the workflow requirements. And each node allocation defines a particle's position and can influence the predicted workflow performance and also the overall efficiency of the system. So another recent work we've done, which was published last year, was to use the RL not only in the profiling, but also in sort of optimizing the resource allocation. So, so we kind of made it a completely RL-based approach of profiling and scheduling, considering the workflow requirements, the preferences, and making sure we're able to optimize this matching of the user preferences to the resources. So I'll talk a little bit next on the other issues, right, that come up in this kind of system in terms of intermittency, reliability, and also privacy security of the workflows. So this work we published last year in IC2E and kind of updated the VC architecture here, as we are showing here, that now we can think of these clusters as a way to deal with the intermittency problem. What I mean by that is I can take a number of volunteer edge nodes and depending on what sort of common QoS profiles they can address, right? So if they all have similar capacity in terms of CPU memory, or they have similar ability to give certain execution times, right? So I can cluster these volunteer edge nodes based on some of these PAX factors, right? So we take that and create this sort of again, using K3S, a number of clusters. And in this problem, what we're doing is we're thinking of intermittency issues. So in that cluster, I'm running certain workflows. What happens if certain nodes fail in that cluster? So can I continue to, finish the execution, right, and have this sort of, again, PAX factors be met at this sort of large scale. So we're doing basically two steps here. Is one is to form similar clusters in the phase one of the scheduler. And in the phase two is basically we're selecting the nodes within the clusters to run the workflows. And the thing that's, again, new in this work is we started adding this whole privacy security aspect to the scheduling of the task. So we're using this idea of confidential computing, where the nodes that actually run have a trusted execution environment. They're going through some hardware attestation, with being monitored to run the workflow. So so there is this extra consideration in running the workflow on a certified node, you can say, right? So I'll talk a little bit more of how we do that, but so that's also something we added. So in terms of not just the intermittency issue, but also ensuring some privacy security of the execution of the workflows, right? And so you can see the kind of technologies we're using. We're monitoring using Prometheus for profiling, for this sort of failover management. We're using a Redis cache and a RabbitMQ queue, and to ensure this sort of security privacy of execution, we're using this confidential computing idea using the open source certifier framework. I'll talk a little bit more about that. And then the testbed is based on, as I said, running functions as a service using OpenFaaS and Docker and all that. So I'll explain the testbed also a bit more. So we're starting with the clustering of the VEC nodes. Then we're basically executing the workflows, considering the intermittency and privacy security issues. And then if there are intermittent failures or availability issues, we're able to sort of recover and ensure execution. So the details of those steps are again shown here. So for creating this sort of clusters of similar nodes, volunteer nodes, we use sort of a capacity-based clustering method using k-means. Using an elbow method, as you can see here, we're able to find the optimal number of clusters given a set of volunteer nodes. And our goal is to do the clustering so that the search latency is small. So if I have an issue with a node or with a cluster, it's easy to find the next best cluster or best node to do the failover, right? So that's sort of the first step. And the second step is to have sort of this scheduling scheme. That's a two-phase scheme for cluster selection using the k-means, and then the node selection based on the availability and the geolocation of these nodes. And then we use sort of a recurrent neural network to predict the availability, and then we use the geolocation because we want to reduce the latency, right, and improve sort of the productivity rate of the workflow execution. And then, last but not least, we are using a test bed to run the convolutional computing paradigm on the workflow tasks and ensure that we can have the privacy preservation as we run these models and data on these nodes. So, so here is the way we implemented this system, right? So we have OpenFast, MicroK8s, and Docker as a way to manage the workflows. And we use a combination of bioinformatics workflows that use deep learning and also certain health informatics workflows that have some machine learning. And they're all basically running as sort of serverless functions. And we have a cloud hub and then the edge integration using these REST APIs and messaging queues. And we have a web interface to basically upload the workflow and manage all of the workflows. So in the testbed, we ran certain experiments with the goal of basically reducing the search latency, the time it takes to identify the most suitable volunteer resources to execute a job, to increase the productivity, right? Even in the face of failures, right? Recovery time being a metric that we're looking at to show how we are able to continue and finish the job execution. And then we had a couple of baselines. One is a Vela paper, which was in IC2E the year before we published, and also the VEC Flex, which is based on the PSO approach we have developed in the past. And so we have a test bed. We actually ran these experiments on to look at search latency and productivity rate, which are defined here. And so you can see here that our approach of this two-phase scheduling, consistently shows better performance in terms of Vela and VEC Flex in terms of the search latency. And so we're able to basically find the right nodes very quickly and do it across a large number of workflow instances. And we're able to achieve twofold reduction in the node search latency compared to Vela, which is the latest state-of-the-art approach to doing this kind of scheduling, and also we're able to show this clustering, approach we have really reduces some of the latency overheads. In terms of productivity, we can show that, again, because we're able to recover faster and have this sort of cluster-based recovery, the two-step process we showed, we can outperform Vela and VEC Flex, right? So it's better in terms of productivity rate, 86.9% compared to 66 for Vela and 65.7 for VEC Flex. So, so we're able to again show at a large scale we can improve the productivity in spite of the failure of the volunteer nodes. And the last part I'll talk about is how we're thinking about this confidential computing paradigm in this context of VEC computing, right? So the issue with traditional computation is, you expose the data, you expose the models on the resources that you're running. So it's easy for somebody who's a resource provider to have access to your model and your data when you're running these workflows. And also the idea of security when you're transporting the data, and most importantly, when the data is in processing, right? How do you ensure that you're having some security privacy during the processing, and last but not least, sharing of the data after it's processed. So all the sort of end-to-end pipeline of data processing requires certain security privacy guarantees, and in a traditional computing environment, that's not given. So how do we create a platform on VEC where we can use some of the, as I said, privacy enhancing technologies to create this sort of expectations for security and privacy for the workflow owner as they run it on volunteer resources. So that's where the confidential computing paradigm comes in, and we were fortunate to work with the VMware group that actually has a very good support system. So they've been sort of guiding us in creating these sort of computing test beds for our VEC experiments, and what the certifier framework, which is part of the implementation they have for confidential computing, is it allows us to provision the sort of TE, right? Isolated enclaves at the hardware level. We can do certain client server encryption. We can do some attestation. We can monitor the computation and make sure the privacy security is being addressed. So as we show here in the left side, the confidential computing basically paradigm with the tools gives us the ability to create the enclaves, have a trusted execution, validate the computation integrity as the processes are running. And then at the end of the day, we want to terminate the enclaves also to make sure the data and the models are all sort of protected, right, at the end of the execution. So overall, end-to-end, we can protect the data in use, basically, right? As the processing is happening, also we can ensure that there is security and privacy on these volunteer nodes. So we've been developing basically a set of tools, we can say, on top of the certifier framework to look at how we can integrate the scheduling part, the data movement for running the VEC workflows, and also we're also looking at how to make the sharing possible of the data once it's processed using some of these confidentiality certification tools. So this is sort of recent work. It's still ongoing, but I think it's an important component we feel in the whole VEC framework. So to conclude, what I have presented is a new way to think about voluntary edge cloud computing for scientific workflows, which builds on some of the initiatives at NSF for storage that we're already seeing, but with the use of K3s, Cubase, and other sort of edge orchestration frameworks, it's possible to Dockerize workflows and really look at scheduling them on these sort of heterogeneous resources. But given the issues of trust, given the issues of intermittency of the resource, given issues of some of the security privacy requirements of the workflows, we needed to build or investigate new approaches and build some tools. That's just what we've been doing. And we've experimented with different kinds of scheduling techniques based on particle swarm, also reinforcement learning. And we are building test beds where we can experiment with different types of edge orchestration, security privacy paradigms like certifier framework, and we're supporting workflows which are very diverse. Right now, we're doing bioinformatics, health informatics, but we want to look at more diverse workflows in maybe manufacturing and other kind of sciences. So that's something we're looking at to expand sort of types of workflows we run on this kind of ideas of VEC computing we have. And also, there's a lot more work to be done in integrating some of these privacy enhancements to the end-to-end processing and sharing on these volunteer edge nodes. So that's also an ongoing work. So with that, I hope we have some time for questions, and I really thank you for your attention, and I'm looking forward to hearing more from you on what we could be doing better.
Thank you. I'm going to go ahead and grab the screen so I can go over some updates from the community. And while I'm doing that, you all are welcome to type in a question. Community updates. Our next webinar will be March 31st at 10 a.m. Central, and our topic is the Trusted CI Operational Technology Procurement Vendor Matrix. So that's a lot of words. We've been calling it the matrix. The purpose of the matrix is to help people acquire new technologies for their projects and ask the right security questions to fulfill the needs of their mission, whatever that is. And so we built this matrix last year, or almost 2 years ago. And we're excited to share it with the community. We want to get more people using it and hearing back about their experiences. So I've got
Jim,
a
yeah.
question. Yeah, let me go ahead and open the chat here and read this. Thanks for your presentation. Does the CC mode require AWS Nitro? Can it use hardware security capabilities, for example, AMD SEV on NSF test beds like Sphere?
Yeah, no, that's a great point. And I mentioned AWS Nitro because for that paper specifically, this was early in our effort with the certifier framework, so we were still having a lot of challenges. So just to prove the concept, we used AWS Nitro because it's already given in the cloud as a way to set up this CC mode. But more recently, in the last 4 to 6 months, we've actually gotten the certifier framework to work. And so that can run on more of sort of any hardware, like you're saying, the NSF testbed like Sphere. And so that's more open source way. And it does it at a software layer. So as long as it's emulating basically a lot of the CC capabilities of, the hardware. So it can run more broadly right now. Yeah, so the paper that I showed you used AWS Nitro because it was early in our project, but more and more we're trying to get the open source certifier framework to work, and there are still challenges. So we're going through it. We're going to the VMware meetings regularly, updating them, getting their feedback. So it's a process we're still working. But the goal is to have it work on any of these NSF resources, testbeds. Yes.
Great, thanks. Any other questions from the audience before we wrap things up? Those of you who are attending this, I will be cutting the video later today and sending it out. So if you want to share it with your colleagues, please do. And with that, any final comments, Prasad?
No, I appreciate all of you coming, and thanks for the opportunity. And Janet, I appreciate you being the host and helping us with this. Thank you all.
Yeah, thank you. Okay, well, have a great day, everybody. When I end this call, you'll all be kicked out of the room. So I'll see you next month. Bye-bye, everybody.
Thank you.